Here in this video, I'll be discussing the system design of e-commerce giants like Amazon or Flipkart. We'll see how they handle millions of users, real-time inventory handling, scalable carts, or seamless order processing at massive scale. We'll break the system into piece by piece and we'll go deep into multiple sections.
First, I'll start with the functional and non-functional requirements. So the first requirements we have is seller can add or onboard items. Next, buyer or the customer can search for items. They can view one item details. They can add item to cart. And the main thing, they can check out or place an order. So placing an order will take care of the inventory management, payment, etc. Next, viewing the order. So customer can see the list of orders they have placed. They can also see the details of a particular order. Here few low priority items I have added, like adding item to wish list, which is similar to adding item to cart. Next, recommend items to user home page. Like when the customer will come to the home page, the customer will see some recommended items. Notify users about order status. So every time the order status will change, the customer will be notified. So the order status will change, like first it will be created, then confirmed, then shipped, delivered, right? There can be more other statuses, but every time the status changes, customers will be notified. Now I will discuss the non-functional requirements quickly. So the first thing is low latency for search or any other user-facing components. High availability for search and any other user-facing components. Next, high consistency for order placement. Orders placements will take care of inventory management, payment, right? These things. So everything should be very consistent. Eventual consistency for item onboarding, search, etc. So it's okay if seller is adding some new item and it's not immediately visible to all the customers. So eventual consistency is fine for item onboarding and search. Next, I have written few main entities here, like item, buyer, seller, cart, order. So this is a massive system, so there will be many more items. If we need more entities, we'll come back and add here. Next, let's discuss the APIs of the system. So first, onboarding the item. So to add one item to the system, we can use a post API with this /items, and the payload will have the item details like name, description, price, quantity, and the item related information. Search items. Search item will be a get API. It will, let's say we have it as /items with the term. Using this term, customer is searching for the items, and this search result should be paginated, right? So for that we are using a cursor based pagination that will have the cursor and the size. Next, adding item to cart. So adding item to cart can be a patch call with /carts, and it will have the item ID and the quantity. Now the user related informations we are not adding in this APIs because user data will be added in the header as an authentication token. So that's for security purpose. We should not add any user details in this payload. Next, checkout API. Checkout API will have the cart ID, the amount, total amount, and the payment info, the payment type, payment method, basically the card number, and if you are using any other payment method, based on that the payment infos will be different. One thing we can notice here in this add item to cart and checkout API, we don't necessarily need to add this cart ID because in the header section anyway we are passing the user details using some authentication token. So we can refer the cart ID from the user information itself. So now let's discuss the scale of the system. So this is, we are talking about Amazon or Flipkart, which is having a huge scale. So we can do the scale related calculations later, but let's just first assume some numbers to get some idea about the scale. So the daily active users, let's say 50 million to 200 million plus. Request per second, it can be 100k to 500k plus during the peak hours. Product catalog, there can be 100 million plus products in the system. Order volumes per day, 5 million to 15 million plus orders will be placed per day, and it will spike during big billion day or any other kind of sales going on. Concurrent sessions, there will be 1 million plus active sessions during major events. Data store, so there will be petabytes of data stored for item, order, and or any other user behavior data. So any kind of user behavior, order status change, everything should be stored in our system. So the data is huge. So this is a huge scale system we are building. So of course we need a microservice based architecture. So first let's see the high level design of the system. So we can see the high level design itself is a very big one. So let's go through it one by one. I'm starting with the basic simple services. So there are different services for different requirements. First, I'm starting with user service. That will handle the accounts, right? User can create account, delete account, or any other account related informations will be stored in this using this user service in this user DB. So user database can be a SQL DB because user informations are very structured. The database should be sharded properly with proper replications and all. Also, each of these service can have its own cache where the recently used informations will be stored. So before going to the database, services can fetch the data from the cache. So for simplicity, I have not drawn the caches here. Now home page. When user will be coming to the home page, the user can see few recommended items. These recommended items can be based on the user previous search history, user previous orders, and the recent order, recent trends, recently added items, and based on few other things. Recommendation service can have a database. We can use a NoSQL database like Cassandra for recommendation database. Next is search service. So that is for user search. So user will search in this search page. This search will be based on some terms or category or anything. So the search service needs to store the information in a database that is good for search. So Elasticsearch database is based for this type of usage. Why? Let's discuss that here. So why Elasticsearch DB for search? So Elasticsearch database stores the inverted index data structure and it makes the text search extremely fast. Now a typical database would need like term, like percentile term, percentile to do this wildcard search, and that is very slow, right? If you are using a SQL database, this query will be very slow. If it is just a prefix search, then SQL DB has indexing and all, it will work fine. But just because we are doing this contains operation, this operation will not use any index in SQL DB, so this query will be very slow. But Elasticsearch does it in milliseconds because Elasticsearch stores the data in inverted index data. Now, Elasticsearch also supports fuzzy matching, partial words, typo tolerance, stemming, synonyms, etc. New data becomes searchable in less than 1 second after being indexed. So because of these reasons, Elasticsearch DB is based for any search. Now come to our search service here. Apart from this Elasticsearch DB, search service also has to talk to this serviceability service. This serviceability service keeps track of whether a particular item can be actually delivered to the particular customer or not, right? So based on the customer location, delivery address, pin code, the serviceability service can decide whether this item can be delivered to the customer or not. Otherwise, it will be very bad experience for the customer that user can see the item in the search results, but user will not be able to place the order for that item. So we should only show the search items in the search results if it is serviceable in that particular location. And how this serviceability service decides that? First, it will talk to the user service to get the user address, pin code and other things. Next, serviceability service will talk to the warehouse service, the actual physical location of the items. It will also talk to the logistics service. Logistics service will have the details of the delivery, right? Delivery partners, how the delivery will happen, how the maps, like how long it will take and all these things. Logistics service will take care of. Similarly here, warehouse service will have its own DB, logistics service will have its own DB. Now this serviceability service can pre-compute the results based on the pin codes and store it in cache, so that when the search will happen, the serviceability service can share the data immediately, because our search needs to have very low latency. Next, let's discuss about viewing item. So customer can go to this item page where they can see the item details. So for that, we'll be using this item service. So item service will store the item related informations in this database. We are using a MongoDB here. We'll see why shortly. Also, the item will also have some images, right? So the images will be stored in this blob storage, and the reference or the URLs of the images will be stored in this database. So now see the item informations. Here for reference, I have taken example of one t-shirt and one TV. So t-shirt will have name, brand, category, descriptions, and there will be few attributes like material, gender, fit, it's regular and all, and the variants of the t-shirts, right? The color of the t-shirt, the size, the images and all. Consider this TV. TV will have this brand category and all, but also it will have the screen size, resolution, panel type, it is a smart TV or not, and other parameters. So the attributes are different for different items, and this is very unstructured informations. So for that, we need some database where we can store this item information in a JSON format. So we are using one MongoDB for that. Next, adding item to cart. So customer can add item to cart from item page. In Amazon, we have seen customer can add item from search page as well. But here, for simplicity, I am considering only from item page customer will be able to add item to cart. So that will be handled by this cart service. So cart service will store the information in this cart database. So cart database will have the cart details, which is ID, user ID. Like for this user ID, this is the cart ID, and the cart was created updated at which time. Next, the cart items information. So for each cart ID, so for each user ID there will be a cart ID. So for this cart ID, which is a foreign key, we'll be adding the items. So item ID with the quantity, and it will have the time when it was added and the price at add. While adding the item, what was the price of the item? So this price can change later. So while adding the item to cart, maybe there was some price, but the customer hasn't placed the order. So if the customer comes back after, let's say, 2 days, the price might change. So this just for audit purpose, we are storing what was the price when customer added the item. So this informations can be used for any other analytics purpose. So we see the cart database tables are structured, but we don't have complex joins here. So we can use some Amazon DynamoDB in this case. Next comes the checkout service. Customer will be able to check out or place order from this checkout page. So this is the checkout service. It will talk to various other services. So first, the checkout service has to check what are the items in this cart. So then it has to talk to this inventory service to check if the if the items are there, if the items are available, then it has to reduce the inventory count. Next, it has to create one order DB entry. In order database, there will be one order database table. There will be, we will be storing this ID, order ID, this the user ID who has placed the order, the amount, the currency, the status of the order. The status will be like created, then confirmed, then shipped, delivered, this type of status of the order. Then payment status, payment method, payment transaction ID, created at, updated at, and so on. There can be few other metadata. So it has to, the checkout service will create one entry in this order DB with status created, let's say. So after that, it will start processing the payment. So for that, it will talk to this payment service. So payment service can talk to some other third party service to actually make the payment. So after payment is done, we'll be changing the order status to confirmed. So now this is a distributed transaction happening here. So this checkout service is talking to multiple service and multiple service, multiple databases update is getting updated, and all this has to happen atomic way, right? So we'll discuss more details in our deep dive section. Next requirements we have is this order view page, where customer will be able to list orders. List orders, and as in what all orders customer has placed previously. Customer can also see the details of a particular order. So that is the view order. So all this will be handled by this order service. It will talk to this order database. So for order database, what type of database we can have for order? For orders database, we should use one relational database which is ACID compliant, and Amazon usually use Amazon Aurora, which is a relational database. Next, let's see the item onboarding flow. So we have seen the buyer actions. Now we'll see how the seller is onboarding new items. So seller can onboard new items using this seller page, and it has to go through multiple services that I have shown here with dots. So there will be item verifications, validations, and other processing for the items. So consider, after all this processing, the new item information is coming in this inbound service. So from this inbound service, several other services has to update its own storage. Why? Because see, in our high level design here, search needs to get the item details from the Elasticsearch DB. Item service has to get the information has to store the item information in this MongoDB. Also, images needs to be stored in this image storage. Warehouse service has to be updated, and let's see few other. Inventory DB also has to be updated with the current quantity of the item onboarded. So several services has to update its own database. So first is search consumer service will read that inbound service information. It will update in this Elasticsearch DB. Inventory service also has to update the inventory count. Item DB has to update the item descriptions, has to store the images of the newly added items. Similarly, warehouse DB also has to be updated. So with this we are good to have our main basic requirements. The item onboarding is done here, and we have seen the buyer actions. Let's see if we have missed any requirements here. Seller can add items, buyer can search items, view item details, add item to cart, check out or place order, view orders, add item to wish list is same as the add item to cart. Recommend items to user home page, notify users about order details. So these few things we need to add, but mostly our major requirements are satisfied here. Now let's discuss the deep dives of this item onboarding flow first. So first of all, this inbound service has to talk to multiple services. And do I need to do it synchronously or asynchronously? It's better to do it in asynchronous way, right? So we'll put this item, newly onboarded item data to in this Kafka queue, and all these services such consumer service, inventory, warehouse, item service, this will read from this Kafka queue and update their databases. Also, the newly added item needs to be part of the recommendations, right? So it has to go through this analytics path and it will go to this recommendation service. So for this analytics, basically we can use one Spark streaming that will aggregate the data for some time, like 30 minutes or 1 hour. Then it will store it in some Hadoop cluster. Then one Spark cluster can run on it, and finally the recommendation service will have the information about this newly onboarded item. Next, let's discuss the order processing flow in detail. So the first is the checkout page. So from where user will be able to check out or place an order. So this will be handled by this checkout service. Checkout service has to talk to multiple different other services and databases. So first it has to check in the inventory service whether the particular item or the list of items, for those list of items, inventory available or not. If yes, then it has to reduce the inventory count. Next, it has to create one order entry or row entry in this order database. So this order database will have this orders table that will have this order ID, user ID, amount, currency, order status, payment informations, and timestamps. So it will create a row here in this table with the status created. After that, it has to initiate the payments. So payment service will call some other third-party service to actually make the payment. Next, after the payment is completed, we can mark the order status as confirmed. If the payment fails, we have to change our order status to be payment failed. So all these things we have to do in our checkout process. So this is basically a distributed transaction. Now first, before I go there, I want to discuss one more thing. Here in this inventory service, when we are checking for the inventory, whether the items are available or not, it can happen that parallel requests are coming together, right? Let's say for one item, only two quantity is available and both the requests came for two items. So if both the requests comes parallelly and we deduct two from the same thing, so this is kind of a race condition are happening. So only two items were left and we actually satisfied four items. So we should not allow that, right? So for that we need to have this serialization for contention. So this database should support serializable property. So if parallel requests are coming, so this request should be treated as serial request, right? One will be satisfied. So first order came, it will reduce the inventory count to 0. Then when the next order will come, it will not be able to satisfy its request. So we'll show an error to the customer. That's one thing. Next, as we discussed, this checkout service is talking to multiple services and databases. So this is a distributed transaction because all this has to happen in an atomic way. So either everything should happen or nothing should happen. Let's say if we deduct the inventory count but the payment is failed, that means the order is not fulfilled, right? But the inventory count is deducted. So that's not a valid scenario. So that's not allowed. That should not be allowed, right? So for this should be in a transaction, distributed transaction. So for distributed transactions, there are different ways to do that using two-phase commit or event-driven saga pattern. But in an Amazon scale, where we have multiple microservices, we have to use some event-based saga pattern. So let's see how it will work. Now this is just an example. User places order. Then checkout service creates order, right? It basically creates on row here with the status created. Inventory service listens to that order created event and reserves the stock and emits one inventory reserved event. Now these two can happen in different order as well. Next, payment service, it listens to inventory reserved event. Then payment service will initiate the payment. After payment is completed, it will emit one payment completed event. Listening to that, logistics service will prepare for the shipment. And it can emit one shipment ready or some other event. Checkout service then listens to that event and it finalizes the order. It changes the order status in the table to confirmed or completed. Completed will be when the order is delivered or maybe it will be confirmed. Now this is the positive part. What happens if, let's say, payment service fails, the payment processing fails? So then payment service will emit one payment failed event. So listening to that, we have to trigger some compensating transactions. Like compensating transaction will be like for inventory service, it will unreserve the stock. Payment service process the refunds. It can happen that from the customer's bank account, the amount is deducted, but the amount is not added to the seller's account or the Amazon account. So in that case, we have to process some refund for the customer. So that payment service will process. Listening to this payment failed event, also checkout service can change the order status to cancelled or payment failed. So this way, this is achieving eventual consistency, and this is not strict atomicity. So we want atomic behavior, but this is a distributed system. We have lots of microservices, so we can achieve this eventual consistency, and this is not strict atomicity, but this is working in atomic way. Let's say the inventory is deducted and payment processing has started, but we haven't received any response further from the payment service. So how long this inventory service should reserve the stocks? There should be a timer for that. So that we achieve using the Redis TTL. Redis TTL is the time to leave. So we'll create this entry for order. This is the order ID, let's say. It created, let's say, at 5, and expiry time is 505. So that means this inventory service will reserve the stock or reduce the inventory quantity for 5 minutes. Within the 5 minutes, if the payment is succeeded, then the status will change. We will change the status to completed or confirmed. So this Redis expiry also has to emit one event. So there are multiple scenarios possible here. First is payment succeeds and then expiry happens. So that means before the expiry, before 5/5, payment succeeds. So that will happen almost all the time. So basically the payment is succeeding, and then the expiry happens, means checkout service will listen to this event when the payment will be succeeded, and it will update the order status to confirm it. Let's say before the expiry, payment fails. So payment service will emit one payment failed event, right? And listening to that, we have to update the order status to payment failed. And inventory service also will listen to this payment fails event, and it will increment the inventory. What will happen if the payment fails after expiry? So let's say that means after 505. Here, after the expiry, also we were emitting one event, right? Listening to the expiry event, we have to update the order status to error or some other different similar status, and also we have to unreserve the stock in the inventory. We have to increment the inventory count. One more scenario is expiry happens at 505, and after that payment succeeds. So this is a tricky scenario, and what we can do in this case, after the expiry, the order status will be updated to error, will increment the inventory back, but then the payment is succeeded. So in this case, we can have a periodic cron job that can refund this amount to the customer. Alternatively, what we can do is, as the payment is already processed, we can create a fresh new order with the payment details. So both solutions are doable. We can discuss with the interviewer and come up with a solution. Here, one thing I want to mention about the Redis TTL. So the expiry time, let's say here is 505, but always the expiry callback will not come at 505. So periodically Redis checks for expired items and then expires those items and sends the callback. So it can happen that the Redis expires this order ID instead of 505, let's say around 507. So in our situation, it's harmless because we will wait for the payments a little longer, so which will not cause any harm here. Now this is how the order placing or the checkout flow works. Apart from that, this checkout service also emit events in some other queue. So there are different other services that has to listen to this checkout. So one thing is notification service. So at any time the order status is changing, let's say order is created, then payment processed, then shipped, then delivered. This type of order status is changing every time. Notification service has to listen to these events and it will send a notification to the customer. Also, this analytic service will listen to this queue and it will listen to this every checkout, every order, and this has to go through this analytics path. And because the recommendation service has to provide some recommendation based on the orders. Like if I am purchasing one TV or laptop, then the recommendation service has to provide recommendation for some other appliances, related appliances. So this order placing or checkout events also needs to go through this analytics path through this to this recommendation sets. That is for user order based recommendation. Now next only one thing is left here, that is the order view page where customer can list the orders or view a particular order details. So that will happen using this order service and it will listen from this order database. Of course, this order database service can have one cache here. I have not drawn it, but it can for first results we can use one cache here. Next, the one thing here, the recently processed orders that are not yet delivered or not yet cancelled, those orders will be in this orders DB. But the already processed orders, already delivered, cancelled or returned order, so after a point of time, we can move those past orders to some archival DB. So there will be some archival service that will move those past orders from this order DB to this archival DB. So when this list orders or view order requests comes, so depending on the request, this order service has to fetch the data from this order database or the archival database. Now one thing I want to discuss quickly is about global distribution strategy. Now consider about Amazon, it's a globally distributed app and it has massive scale. So what are strategies we can apply here? So the first thing is global replication of data. Like the tables, global tables will have read replicas. Next is read from the nearest region. Next, use edge caching like Redis or CDN for static data like product information, prices, images. Next, use region-based sharding for the databases. Next, route user requests to the closest region. Next, we can replicate updates asynchronously for eventual consistency. Here one example we have is, consider user in India clicks on a product. Request routed via Route 53 DNS to Mumbai region. Product info fetched from the DynamoDB and the static data is fetched from the CDN or cache. Next, inventory can be validated from local shard as the databases are sharded regionally, so we can validate the inventory from local shard. Recommendation engine can send the personalization via Kafka, so that this should happen asynchronously. So this is a massive microservice architecture. We have to see wherever possible we have to implement event driven architecture. Mostly everything has to happen asynchronously. Now let's quickly see the functional and non-functional requirement we had here, and at functional requirements we have satisfied all, and non-functional requirements: low latency for search, high availability for search, high consistency for order placement, eventual consistency for item onboarding, search, etc. All these are satisfied. So I think we are good with the system design of Amazon or Flipkart now.